In this video, we are going to talk about diagonalization. This video, as well as the matrix, all the videos in this chapter, applies to square matrices only. So don't try to diagonalize a non-square matrix. And while I'm kind of on a little diatribe, don't try to use the invertible matrix theory on a non-square matrix because the invertible matrix theory applies only to square matrices. Okay, back to our topics. So here is our overview slide, which we will spend 3 or 4 minutes discussing before we go through each topic with more detail and more examples. First, we'll define a diagonal matrix, which is a square matrix whose non-diagonal entries are all 0. Then we'll talk about diagonalizing a matrix. To diagonalize a matrix, you're going to find if A is similar to a diagonal matrix, that is, using our definition of similarity, which we'll review, A then will be equal to an invertible matrix P times our diagonal matrix D times P inverse. From there, we have several theorems to tell us when a square matrix is diagonalizable. First, an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. Our next theorem tells us n distinct eigenvalues is sufficient for diagonalization. And then we have this last theorem here, which says that, a matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. And then last we have this other theorem, if A is diagonalizable and B sub k is a basis for the eigenspace corresponding to the kth eigenvalue, lambda k, for each k, then the total collection of eigenvectors in the set b1, b2 up to bk forms an eigenvector basis for Rn. And I do also have the summary of when is a matrix diagonalizable. But first we have the definition of what it means to be diagonalizable. That is, it's diagonalizable if A is similar to a diagonal matrix D. But more to the point, a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. This next theorem, if you happen to have distinct eigenvalues, then there's a simplification. You don't have to check that your eigenvectors are linearly independent because eigenvectors associated with distinct eigenvalues are always independent. So this theorem here simplifies. If you have distinct eigenvalues, you don't have to check for independence. You get that for free. But what if you don't have distinct eigenvalues? That's this last theorem here. Actually, this part here is interesting, but as far as whether or not it's diagonalizable, we're only going to look at part 2. So I'm going to get rid of part 1 in this list. So if the matrix has distinct eigenvalues lambda 1, lambda 2 up to p, which is less than n, then the matrix is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. And we'll look at examples. But this is my summary of when is a matrix diagonalizable. So that concludes the overview. And so now we're ready to go back and address each topic in more detail with more examples. First, we will start by defining what a diagonal matrix is, and that's a square matrix, an n by n matrix whose non-diagonal entries are 0. Here we have an example of a diagonal matrix. The diagonal, along the main diagonal, we have the entries 5 and 3. Everywhere else, we have zeros. And one thing to note, the first kind of application we're going to do is powers of a diagonal matrix are easy to compute. So in particular, let's look at this D here, the 5003. D squared then will equal 25009, and you can compute then D cubed, which is just D times D squared. You'll see that that will be 5 cubed, 0, 0, and then 3 cubed. So in general, you'll find the pattern is D to the kth power if D is diagonal, and D is for diagonal. That would be equal to your entries along the diagonal raised to the kth power, and your zeros stay 0. So d sub k in this case, for our example, is 5 to the k 0, 0, and 3 to the k. So that's kind of neat, but is it useful? And later we should be doing some examples from differential equations that do use this powers of the diagonal matrix. We'll look at a more complex example where we have the matrix A is equal to the matrix with column vectors 7, -4, 2, 1. We're given this P, which is an invertible matrix, which is equal to 1, negative 1, 1, negative 2, and a diagonal matrix that we had looked at before, 5, 0, 0, 3. We can note that A is equal to P times D times P inverse, and I'll let you confirm that for yourself. But now we want to find A raised to the K, a general formula for this. I'm going to start by calculating P inverse. To calculate P inverse, I take my matrix P, my 1, negative 1, 1, negative 2, and I put it alongside the identity matrix. Then I'm going to do row operations until my original matrix P becomes the identity matrix. And while I row reduce the whole thing together here, my identity matrix will become P inverse. So P inverse in this example would be 2, negative 1, 1, negative 1. And I'll leave it to you to verify that A, my matrix A, is equal to P, D, P inverse. And now next we're going to find A raised to the K. Because I can write A as P times a diagonal matrix times P inverse, and the kth power of a diagonal matrix is easy to compute, we'll see that A to the K is also easy. So I start looking at A squared, and I'm going to keep this in terms of symbols and general formula instead of working with this particular example, and you'll see why in a minute. So A squared, I'm going to write my A as P, D, P inverse. So P, D, P inverse times P, D, P inverse. And now, because while matrix multiplication is not commutative, it is associative. So I can associate the P inverse with P here. So now I'm going to have PD, P inverse times P, and then dP inverse. Now this P inverse times P now becomes equal to I, so I'm left with PD and then dP inverse, and this is d squared in the middle. So A cubed now becomes A times A squared, so I've written A here, and then my A squared, I have P d squared P inverse. Again, these two can be associated together, and that will give me I. So now I'm going to have P d cubed P inverse. So my formula for A to the K then is going to be P d to the K P inverse. So I have written my P, my d to the K, and P inverse, and I've did the multiplication out here to get this matrix here. So again, the idea is, one, the powers of a diagonal matrix, D raised to the K, that's easy to compute. But also, if you have a general matrix that's not a diagonal matrix, if you can get it to this form, where it's P times a diagonal matrix times P inverse, then the calculation of A to the K is also fairly simple. So a couple of things to say about the last example. First, I wrote the formula for A raised to the K that we found, which is P d to the K, P inverse to the K. And next, I want to look in particular, if A is not a diagonal matrix, when is it easy to calculate A to the K? It's easy when you can write A in this form, P times a diagonal matrix times P inverse. And I want to focus on this definition of similarity that we had seen in the previous video, but really spent very little time on this. So this form here, when A, not a diagonal matrix, is easy to compute A raised to the K, is exactly when A is similar to a diagonal matrix. And we can see that because reviewing our definition of what it means for two matrices to be similar. So if A and B are n by n matrices, then A is similar to B if there's an invertible matrix P such that P inverse A, P equals B, or equivalent, A equals P, B, P inverse. So again, this definition here is saying that A over here is similar to a diagonal matrix. Before I leave this idea, I just want to show that these two, I'm going to circle them in green now, these two expressions are the same because we have P inverse A, P equals B from over here. I can multiply both expressions, this side of the equation and the right side of the equation, by P on the left side. So I multiply P times P inverse AP and P times B. It's very important that you stay on the left side because remember, matrix multiplication is not commutative. Similarly, I can multiply now this expression, both sides of the equation, by P inverse on the right-hand side. And now, again, I can group. Matrix multiplication is associative. So I have my I matrix here and my identity matrix here. So I finally just get A on the left-hand side. And on the right-hand side, I keep P, B, P inverse, which is exactly this expression here. And again, the reason why I wanted to talk about similarity is because this definition of diagonalizable means that A is diagonalizable, or we say it's diagonalizable, if A is similar to a diagonal matrix. So if you can diagonalize a matrix, then the matrix is similar to a diagonal matrix. Next, we have our first theorem that tells us when a matrix is diagonalizable. And this one says an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. And in fact, it tells us how to find P and D, the invertible matrix P and the diagonal matrix D, that A is similar to. And in particular, the columns of P are the n linearly independent eigenvectors, and then the diagonal entries of D are the eigenvalues of A. I moved this theorem over here so I can do the proof. I'm not going to be doing the entire proof, but enough of the proof to get a feel for what's going on and how we're going to use the eigenvectors and eigenvalues to find P and D, or to construct P and D. And I have one note that I'm going to use in my proof, but let's review that before we get to it. So if P is any n by n matrix with column vectors v1, v2 up to vn, and if D is any diagonal matrix with diagonal entries lambda 1, lambda 2 up to lambda n, then if we multiply a matrix A times the matrix P, that would be equal to A times the matrix with column vectors v1, v2, vn. Remember, we said P is the matrix with these column vectors, which is equal to then AV1, AV2 up to AVN. So this is one point we're going to use later in our proof. And then also P times D, if P is a diagonal matrix, we have P and we have the diagonal, is going to equal to our lambda 1 v1, lambda 2 v2 up to lambda n vn. And I kind of did the 3 by 3 matrix example just to give just so we can kind of see how this came about. Here we have P with our column vectors v1, v2, and v3. And I have to warn you, normally this is v11 and this indice is v12 because our indices are row and column, but I am doing this as column vectors. So my first column vector is v11, v12, and v13. My second column vector is v21, v22, v23, and my third column vector is v31, v32, and v33. So column vector 1, 2, and 3 correspond to this. So the indices look different. But anyway, I have my 3 vectors in a matrix times then my diagonal, which has my eigenvalues on the diagonal of my 3 by 3 matrix. And you can see when I do the multiplication, I multiply row times column, I'm going to get lambda 1 v1 and then 0, 0. Over here, this row times this column is going to pick out my lambda 2 times v21, and then the other things are multiplied by 0. And then finally, I have my lambda 3 picking out my v31. And you can see I do the next row and then the other multiplications. And what I get is lambda 1 times my first column vector, lambda 2 times my second column vector, and lambda 3 times my third column vector. So this fact here, I will be using in our proof. As I had mentioned, I'm not going to prove the entire theorem, but I am going to start by proving if A is diagonalizable, then, that's the forward direction of this if and only if, then A has n linearly independent eigenvectors, and we're going to use these to be our column vectors of P. We are going to start with the fact that we are given A is diagonalizable. So suppose A is diagonalizable, that is A is similar to a diagonal matrix D. So A is equal to P times D times P inverse. And if I multiply both sides of this equation by P on the right-hand side, I'll get AP is equal to dP P inverse times P. These two, the P inverse times P, becomes the identity matrix, and I get AP equals PD. And now using what we had written over here, then over here on the left-hand side, I have A times P is equal to AV1, AV2 up to AVN. And on the right-hand side, I have P times D is equal to lambda 1 V1, lambda 2 V2 up to lambda n Vn. Now I'm going to equate column by column, so my AV1 is equal to lambda 1 V1, my AV2 is equal to lambda 2 V2, up to AVN is equal to lambda n Vn. But each of these n equations tells us that we have an eigenvector-eigenvalue pair. You can see that this is the equation for an eigenvector v1 with eigenvalue lambda 1. In particular, v1 and lambda 1, v2 and lambda 2, and vn and lambda n, those are n eigenvector-eigenvalue pairs. So now we have our n eigenvectors from A diagonalizable. Also, because P is invertible, its column vectors, which we're going to use as the eigenvectors, are linearly independent. As I had mentioned, I'm not going to prove this entire theorem. I only proved this first part, the forward direction. I haven't proved the other direction. That is that if A has n linearly independent vectors, then A is diagonalizable. This one I'm just going to have you use this part of the theorem without proof. But what we do have from this proof is that if we have n eigenvectors, v1, v2 up to vn, we're going to use those eigenvectors to construct the columns of P, and we're going to use the corresponding eigenvalues, lambda 1, lambda 2 up to lambda n, to construct D. And then if AP equals PD, if the eigenvectors are linearly independent, then P is invertible by the invertible matrix theory, and AP equals PD, which gives us that A is similar to our diagonal matrix. And again, this last statement, we're going to use n linearly independent eigenvectors to construct the columns of P and use the corresponding eigenvalues to construct D. We're going to add this to our overview slide. This theorem then is the first theorem we can use to check if a matrix is diagonalizable. That is, it's diagonalizable if and only if A has n linearly independent eigenvectors. And before we add this, let's go ahead and do an example. We want to diagonalize the following matrix if possible. That is, we want to find the invertible matrix P and the diagonal matrix D such that A is similar to that diagonal matrix D, where A is equal to the matrix with column vectors 1, negative 3, 3, 3, negative 5, 3, and 3, negative 3, 1. We're going to find the eigenvectors to construct P, and we use the eigenvector equation, AX equals lambda x. Again, eigenvectors are those vectors x when multiplied by A just gives you a scalar multiple of x. Subtracting lambda x from both sides of the equation, we get ax minus lambda x equals 0, and introducing the I, we have a minus lambda I x equals 0. So our augmented matrix for this a minus lambda I x equals 0 is the matrix 1 minus lambda minus 3, 3, 3 minus 5 minus lambda 3, 3 negative 3, 1 minus lambda, and 0, 0, 0. To find the lambdas here, or when this homogeneous equation has solution, we're going to look at the determinant of the matrix A minus lambda I. So here is my determinant of A minus lambda I, just keeping it here. 1 minus lambda minus 3, 3, 3 minus 5 minus lambda 3, 3 negative 3, 1 minus lambda. So I have my first A1, 1. So 1 minus lambda, crossing out. Then, since we're taking this term, we're going to cross out that row and that column, and we're left with the determinant of this matrix here, my minus 5 minus lambda, 3, and then minus 3, 1 minus lambda. Next, we're going to go across for the next element in the first row, and we alternate signs. So this is a minus 3, crossing out then this row and this column. We're left with the determinant negative 3, 3, and negative 3, 1 minus lambda. Finally, we take this last element of the third row, 3, crossing out that row and column. we get this determinant, negative 3, 3, negative 5 minus lambda, and 3. Then here, for the 2 by 2 determinants, I just do the cross multiplication. So I have 1 minus lambda, cross multiplying minus 5 minus lambda times 1 minus lambda, and then minus this cross multiplication, which is negative 9, so I get a positive 9. I have my negative 3 cross multiplying negative 3 times 1 minus lambda minus the cross multiplication of negative 9, so I get a positive 9. Finally 3, and then my minus 3 times 3 is minus 9, and then minus 5 minus lambda times 3. And then to get this expression over here, I used Wolfram Alpha online. So you can plug in your expression. So I plugged this in, I put in x instead of lambda, and then it gave me a number of equivalent algebraic statements, and I chose this one because this is the one, the minus 1 minus lambda, lambda plus 2 squared. This tells me that my eigenvalues then are lambda equals 1 and lambda equals negative 2. I moved my eigenvalues here, lambda equals 1 and lambda equals negative 2. I have my matrix equation here and my augmented matrix associated with that. So I'm going to use this augmented matrix to find my eigenvectors associated first with lambda equals 1, and then I'll do the same thing for lambda equals negative 2. Then plugging in lambda equals 1, so 1 minus 1 is 0, and then my minus 5 minus 1 will give me my minus 6. My 1 minus lambda gives me 0. So this is my diagonals. The rest of my matrix I just carried over. I'm going to row reduce my augmented matrix now until I finally get this matrix here, which tells me that x2 must equal to minus x3, and x1 is equal to, well, minus x3 minus 2x2, which is just equal to x3. So in other words, if I let x3 equals 1, the vector x1 is equal to x3 is 1, x2 would be minus 1, and again I let x3 equals 1. So the 1 minus 1, 1 is a basis for my lambda equals 1 eigenspace. And also this is my 1 minus 1, 1 is my eigenvector associated with lambda equals 1. I write my first eigenvector eigenvalue pair here, and now I'm going to plug in my next eigenvalue, lambda equals negative 2. Plugging in negative 2 into this matrix, augmented matrix, across the diagonal, I'll have 1 minus negative 2, which will give me 3. I have my minus 5 minus negative 2, which will give me negative 3. And then 1 minus negative 2 will give me positive 3. And all the other entries I just copy over. Row reducing thus, what I get is that x2 and x3 are free, and x1 is going to equal to minus x2 minus x3 over here. Writing out the solution then, I have x1 is equal to x2 minus x3. I have x2 and x3 are free. So a basis then for this set of vectors is negative 1, 1, 0, and negative 1, 0, 1. So these two vectors will be my bases for the lambda 2 equals negative 2 eigenspace. So here I have my 3 proposed eigenvectors. I want to verify that they're linearly independent because I do have this theorem here that says if I have 3 linearly independent eigenvectors, then A will be diagonalizable. And then I can use my n linearly independent eigenvectors to construct the columns of P. So what I have here is my first eigenvector, 1, negative 1, 1, my second eigenvector, negative 1, 1, 0, and my last eigenvector, negative 1, 0, 1. And I look at the homogeneous equation. I want to know whether or not there are non-trivial solutions. So I row reduce, and what I get is x1, x2, x3 equals 0, which means that my 3 vectors are linearly independent. So I'm just going to note that here, that these 3 eigenvectors are linearly independent, which means I can use these 3 eigenvectors to construct columns of P. So P now is equal to my 3 eigenvectors, 1, negative 1, 1, my second eigenvector, negative 1, 1, 0, and my last eigenvector, negative 1, 0, 1. D is going to have on its diagonals the eigenvalues. So my eigenvalues are 1 and 2, And actually, this 2 I should have noted was multiplicity 2. Just to remind you, when we found the determinant was -1 minus lambda, lambda plus 2 squared. So this lambda equals -2 eigenvalue has multiplicity 2, so I need it on 2 of my diagonal entries. I kind of would have thought to diagonalize, I would also need to calculate P inverse, since I want to satisfy the equation A equals P times D times P inverse. But in this, in the problem, and also just looking at the solution, really they just want to find a P and a D matrix that satisfies this equation, but then to verify it satisfies this equation, your book says, well, we can then make the task simpler by multiplying both sides of this equation on the right by P. So now instead of A equals P D P inverse, I have AP times P D P inverse times P. So again, I multiply both sides of the equation by P. I can group these two together, and I got AP equals PD. So in other words, instead of finding P inverse, just to make things a little easier, we can just verify that this calculation works, in which case we will have found our matrix, our invertible matrix P, and our diagonal matrix D. And so that's exactly what I did here. I multiplied A times P, and I multiplied P times D, and I get the same matrix. So I have verified that I have calculated my P and D correctly. I have my next example is to diagonalize the following matrix if possible. A is equal to the matrix with column vectors 2, -4, 3, 4, -6, 3, 3, -3, 1. Starting as I had in the previous example, we want to find the eigenvectors to use to construct P. To find the eigenvectors, we start with the eigenvalues. The equation we use to find eigenvectors and eigenvalues is the AX equals lambda X equation. So A operating on X will just give you a scalar multiple lambda times X. Subtracting lambda X from both sides, I get AX minus lambda X equals 0. Introducing the I then, I have A minus lambda I X equals 0. So this is my augmented matrix. I subtract lambda on the diagonal, so I have 2 minus lambda, 6 minus lambda, and 1 minus lambda on the diagonal, and then the other entries remain the same. To take the determinant of this part, not the augmented matrix, but this part of the matrix, I have that done here. So I have my 2 minus lambda times the determinant of my -6 minus lambda, 3 minus 3, 1 minus lambda. Then I have my 4, minus 4, times the determinant of my -4, 3, my 3, 1 minus lambda, and then finally 3 times the determinant of -4, 3, and -6 minus lambda, 3. Finishing my determinant calculation, I have my 2 minus lambda cross multiply. I get -6 minus lambda times 1 minus lambda plus 9. My -4 cross multiplying, -4 times 1 minus lambda plus 9, and then 3, my -12 minus 3 times -6 minus lambda. And to save me from having to do this algebra, I again used Wolfram Alpha online. I put in this expression using x instead of lambda, and it gave me a number of equivalent expressions, and this is the one I chose to use, and it gave it to me with x's, but I put in my lambda, so it's minus lambda minus 1, lambda plus 2 squared. So in other words, lambda equals 1, and lambda is equal to -2. I moved my eigenvalues here, and I kept my augmented matrix for A minus lambda I x equals 0 over here. I'm going to use this now to solve for x when lambda equals 1, and then afterwards I'll plug in lambda equals -2. For lambda equals 1, I get the augmented matrix with column vectors 1, -4, 3, 4, -7, 3, 3, -3, 0, and then 0, 0, 0. Again, just looking at the diagonal, I had plugged in lambda equals 1, so I get 1, -6 minus 1 is -7, and 1 minus 1 is 0 on the diagonal. Everything else is the same. I row reduce until I get that x2 is equal to -x3, and x1 is equal to -x3 minus for x2, which is just equal to x3. So in other words, 1 minus 1, 1 is our eigenvector associated with this eigenvalue lambda equals 1, and it's also a basis for the lambda equals 1 eigenspace. I'm going to make note of my eigenvector eigenvalue pair, lambda equals 1 and 1 minus 1, 1. And I'm going to do the same thing. I'm going to use this matrix now on lambda equals minus 2. Plugging in lambda equals minus 2, I am going to get the augmented matrix 4, negative 4, 3, 4, negative 4, 3, 3, negative 3, 3, 0, 0, 0, which reduces to this matrix here, which tells me that x3 is equal to 0, x2 is free, and x1 is equal to minus x2. So my x1, let's see, x3 is 0, x2 is free, so I'm going to let that equal to 1, and then x1 would equal to negative 1. So now negative 1, 1, 0 is a basis for the lambda equals minus 2 eigenspace. So now I have my next vector eigenvalue pair, lambda equals negative 2 with vector negative 1, 1, 0. But according to my theorem, I need, since this is an R3, my vectors are three-dimensional, I need 3 linearly independent eigenvectors. But I'm not going to be able to get that for A because my spaces for my eigenspace for lambda equals 1 is one-dimensional. My eigenspace for lambda equals minus 2 is also one-dimensional. So I can only cover 2 dimensions. I don't have a way of creating a third linearly independent eigenvector. I can add 2 of these together to get a third eigenvector. I can scalar multiply either of these by some scalar and get another eigenvector, but they won't be linearly independent. Therefore, A, according to this theorem, is not diagonalizable. Our next theorem gives us a sufficient condition for diagonalization. That is, n distinct eigenvalues is sufficient for diagonalization. The theorem in particular says an n by n matrix with n distinct eigenvalues is diagonalizable. I moved my theorem up here to give us some space for a proof. We're going to start with the fact that we are given we have n distinct eigenvalues, and we have this theorem that talked about the independence of eigenvectors. So if v1, v2, vp are eigenvectors that correspond to distinct eigenvalues, the n distinct eigenvalues of an n by n matrix, then the set of v1, v2 up to vp is linearly independent. Since then our n distinct eigenvalues have associated with eigenvectors, and in particular each eigenvalue has an eigenvector associated with it, we have n total eigenvalue eigenvector pairs, and according to this theorem, because the eigenvalues are distinct, the n eigenvectors must be linearly independent. And then according to our previous diagonalization theorem, an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. So according to this theorem, this means our matrix is diagonalizable. So here's the theorem: an n by n matrix with n distinct eigenvalues is diagonalizable. And we want to note it's not necessary for the matrix to have n distinct eigenvalues to be diagonalizable. This theorem is different from this other one here, which was an if and only if. This is just an if-then kind of theorem. In particular, this theorem says if there are n distinct eigenvalues, then it is diagonalizable. So sort of this implication here. This note here is saying it is not that if it's diagonalizable, you can't go the other way. It's not the converse. Diagonalizable implies n distinct eigenvalues. That is not, this converse statement is not necessarily true. Sometimes it's true and sometimes it's not. And in fact, we had the example where A was equal to 1, negative 3, 3, 3, negative 5, 3, 3, negative 3, 1, and we only had 2 eigenvalues. The third eigenvalue, this lambda equals negative 2, was had multiplicity of 2, but we were still able to find P and D, and it was indeed diagonalizable. And looking at this statement, again, this theorem rewritten as n distinct eigenvalues implies diagonalizable and contrasting it with the converse, which is saying diagonalizable implies n distinct eigenvalues. So this one isn't necessarily true, even though this one is. It's the difference between necessary and sufficient. Here, necessary and sufficient. So here, this statement, n distinct eigenvalues implies it's diagonalizable, is the same thing as saying if you have n distinct eigenvalues, that's sufficient to guarantee that your matrix is diagonalizable. That is not the same as diagonalizable guarantees n distinct eigenvalues. In fact, you can have n distinct eigenvalues, and it's not necessary for diagonalization. That's what this is. So again, it's the difference between being necessary and sufficient. So that's why I have in this description of the theorem, I said that n distinct eigenvalues is sufficient for diagonalization. So I'm trying to keep track of the theorems that tell us when a matrix is diagonalizable. So far we've had this first theorem here that said a matrix is diagonalizable if and only if A has n linearly independent eigenvectors. And then we just covered this theorem here that says that a matrix with n distinct eigenvalues is diagonalizable. And these two theorems are related. There are two differences. First, this is an if and only if, whereas this is an implication, so it's the converse is not necessarily true. But the second thing is, here you have to assure that your eigenvectors are linearly independent. In this theorem, you don't have to, because we have this other theorem from the video when we discussed introduced eigenvectors and eigenvalues. We said eigenvectors associated with distinct eigenvalues are linearly independent. So that means here, if you know you have distinct eigenvalues, the eigenvectors are automatically independent. So that's one less thing you have to check if you know you have distinct eigenvalues. Our next topic is to look at matrices whose eigenvalues are not distinct. In particular, we have this theorem. Let A be an n by n matrix whose distinct eigenvalues are lambda 1, lambda 2, up to lambda p. And the idea is that p might be less than n. Then for k between 1 and p, the dimension of the eigenspace, lambda k, is less than or equal to the multiplicity of the eigenvalue. And 2, the matrix is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. So let's move this up, give us some space, and look at an example. So here's our theorem. A is an n by n matrix with distinct eigenvalues, lambda 1, lambda 2, up to lambda p. P might be less than n. Let's look at this first statement. For k less than or equal to 1 and greater than or equal to p, the dimension of the eigenspace lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. So let's refer to the example we had worked earlier in this video, where A was the matrix with the column vectors 1, negative 3, 3, 3, negative 5, 3, and 3, negative 3, 1. We had found the eigenvectors by taking the determinant of A minus lambda I. So across the diagonal, we subtracted minus lambda. And then we found the determinant would be equal to negative lambda minus 1, lambda plus 2 squared. And we set that equal to 0 to find where this matrix has eigenvalues. And what we found was the first eigenvalue was 1, and then we had the eigenvalue equals negative 2, and that had multiplicity of 2. So in this case, we're in R3. Our vectors is a 3 by 3 matrix, but we only have 2 distinct eigenvalues. And then for each eigenvalue, the dimension of the eigenspace is less than or equal to the multiplicity. So for lambda equals 1, we found the basis of one vector, 1, negative 1, 1. So the dimension of this eigenspace was equal to 1, which is exactly the multiplicity of lambda. And here we have for lambda 2 equals negative 2, this was our basis for our eigenspace. So the dimension of the eigenspace is also equal to 2. And here we're saying the dimension has to be less than or equal to the multiplicity, which falls in line right here. The next statement from this theorem, the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. So here the dimension of this eigenspace is 1, the the dimension of this eigenspace is 2 because there are two basis vectors. So 1 plus 2 is 3, which is exactly equal to n. And that's how we were able to find, or why we were able to find our invertible matrix P and our diagonal matrix D for this example. And again, keeping track of when is a matrix diagonalizable, now we have it's diagonalizable if and only if A has n linearly independent eigenvectors, or when we know that the eigenvalues are distinct, we get the independence of the eigenvectors for free. But if we don't have n distinct eigenvalues, we have our new theorem here. So if we have p distinct eigenvalues, where p is less than n, then the matrix is diagonalizable if and only if the sum of the dimension of the eigenspaces equals n. This last theorem is sort of like a bonus theorem. So if A is diagonalizable and B sub k is a basis for the eigenspace corresponding to lambda sub k for each k, then the total collection of your eigenspace vectors forms an eigenvector base for Rn. Here I've moved the theorem to the top of the page again, and I have the previous example we had done with A equal to 1, negative 3, 3, 3, negative 5, 3, 3, negative 3, 1. Our first eigenvalue, eigenvector pair was lambda equals 1 with bases 1, negative 1, 1 for the eigenspace. And our next eigenvalue was lambda equals 2. And the basis for the eigenspace is negative 1, 1, 0, negative 1, 0, 1. According to this theorem here, so we have bk as a basis for the eigenspace lambda k. So this is lambda 1, so b1 is equal to 1, negative 1, 1. And then this is lambda 2, so b2 is equal to negative 1, 1, 0, negative 1, 0, 1. According to this theorem, then the total collection of the vectors forms a basis for Rn. So in other words, these three vectors then form a basis for Rn. And again, this theorem is because A is diagonalizable. So this is a basis. We don't have to check that they're linearly independent. If we didn't know A was diagonalizable, then we would. Our next example is determine if the following matrix is diagonalizable. That's the matrix A with column vectors 5, 0, 0, negative 8, 0, 0, 1, 7, 2. And note that this is a triangular matrix. We use this theorem here. The eigenvalues of a triangular matrix are the entries on its main diagonal. So this matrix is triangular, so the diagonal entries are 5, 0, 2. So in other words, our eigenvalues are lambda 1 is equal to 5, lambda 2 is equal to 0, and lambda 3 is equal to 2. So we have three distinct eigenvalues, which according to a theorem that we had gotten when we first talked about eigenvectors, eigenvalues, if the eigenvalues are distinct, then the associated eigenvectors are independent. So we'll have three linearly independent eigenvectors. Then to finish, we have our diagonalization theorem that says an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. Since n is equal to 3, because A is 3 by 3, we have three linearly independent eigenvectors. According to this theorem, that means A is diagonalizable. Our next example is to diagonalize the following matrix if possible. So A is a 4 by 4 with column vectors 5, 0, 1, negative 1, 0, 5, 4, negative 2, 0, 0, negative 3, 0, and 0, 0, 0, 3. And this is also a triangular matrix. It's really good to be able to see this because it simplifies this part of the work greatly. So our eigenvalues are lambda equals 5 with multiplicity of 2 and lambda equals minus 3 with multiplicity of 2. I'm going to write my eigenvector equation, which is ax equals lambda x, right? Our eigenvectors are those that when you multiply by a only gives you a scalar multiple of your original vector x. So then subtracting lambda x from both sides, I get ax minus lambda x equals 0. Introducing my I get a minus lambda I x equals 0. So my augmented matrix will look like this. I've subtracted my lambda I, So I subtracted lambda across my diagonal, 5 minus lambda, 5 minus lambda, minus 3 minus lambda, minus 3 minus lambda, and the rest of the matrix is the same. I'm going to use this matrix here now to find the eigenvectors associated first with lambda equals 5 and then lambda equals negative 3. We start by plugging in lambda equals 5 into this matrix. So my 5 minus lambda will be 0, and my minus 3 minus lambda will be equal to minus 3 minus 5 will be minus 8. So here is my starting matrix. So I'm going to solve the homogeneous equation. I row reduce, and I find that x3 and x4 are free. x2 is equal to 4x3 plus 4x4, and x1 is equal to minus 8x3 minus 16x4. So this is the general form of my solution for the homogeneous equation a minus lambda I x equals 0. It's equal to minus 8x3 minus 16x4, that's x1. Then I have 4x3 plus 4x4, that's x2, and then x3 and x4 are free, which means that my minus 8, 4, 1, 0 and minus 16, 4, 0, 1 form a basis for the eigenspace associated with lambda equals 5. I'm going to do the same thing to find the basis for the eigenspace associated with lambda equals negative 3. So I start by plugging in negative 3 for lambda in my augmented matrix. So 5 minus negative 3 will give me 8, and my negative 3 minus negative 3 will give me 0. So I plug that negative 3 in for lambda, and this is the augmented matrix I get. It's the 4 by 4 with column vectors 8, 0, 1, negative 1, 0, 8, 4, negative 2, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0. So many zeros. It doesn't take much to row reduce until I finally get this matrix here with column vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0. This one's pretty easy to solve, so I see that x3 and x4 are free, and that x1 and x2 are equal to 0, so my 0, 0, 1, 0 and 0, 0, 0, 1 is a basis for the lambda equals x3 eigenspace. I've cleared some stuff out. I have the basis for my eigenspace associated with lambda equals 5 right here, and I have my basis for my eigenspace associated with lambda equals 3 over here. And the first thing we're going to look at here, the sum of the dimensions of the eigenspace equals n. So here, my eigenspace lambda equals 5, there are two basis vectors, so the dimension is 2. Here, my eigenspace for lambda equals 3 has two basis vectors, so the dimension is equal to 2. So 2 plus 2 is equal to 4, which is exactly equal to n. So according to this theorem here, A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. So it is diagonalizable. And we form our invertible matrix P with these eigenvectors, negative 8, 4, 1, 0, negative 16, 4, 0, 1, and 0, 0, 1, 0, and last 0, 0, 0, 1. And the diagonal matrix is just the matrix with the eigenvalues on the diagonal. So 5 appears twice because it has multiplicity of 2. And the 3 also appears twice because it has multiplicity of 2. I'm sorry, that's negative 3 because it has multiplicity of 2. And last, from the second part of this, then our collection of bases for each eigenspace can form a basis for Rn. So in other words, our 4 eigenvectors then will be a basis for R4. Now that we have covered our topics for this video, I have 3 more questions for you, but since we've covered all topics, I'm going to suggest that at the end of each problem statement that you pause the video to give the problems a try before you look at the solutions. The first question is to compute a to the 8th, where a is equal to 4, 2, negative 3, negative 1. For this problem, you want to get A in this form, where A is similar to a diagonal matrix. In particular, A is equal to an invertible matrix P times D times P inverse. So to get these matrices P and D, we're going to find the eigenvalues and eigenvectors. So first I have my eigenvector equation. So a vector x is an eigenvector if ax is equal to a scalar times x. Subtracting lambda x from both sides, I get ax minus lambda x equals 0. And then introducing I get a minus lambda I x equals 0. So a minus lambda I is the matrix where you subtract lambda from the diagonal. 4 minus lambda, minus 3, and 2, minus 1 minus lambda. So here's our matrix. To determine when this system has solution for the homogeneous equation, we look at the determinant. So looking at 4 minus lambda 2, and then minus 3, minus 1 minus lambda, cross multiplying, we get 4 minus lambda times minus 1 minus lambda minus our negative 3 times 2, which gives us a positive 6. So this becomes lambda squared minus 3 lambda plus 2, which we factor into lambda minus 2, lambda minus 1. Setting that equal to 0, that means we have lambda equals 2 and lambda equals 1. Plugging in lambda equals 2 into our eigenvector equation in order to find the eigenvectors associated with lambda 2. So here plugging in 2, 4 minus lambda is 2, and then we have a minus 3, we have a 2, and then minus 1 minus our lambda 2 is equal to minus 3. And then to solve the homogeneous equation, we have our augmented matrix with 0, 0. Row reducing, we get x2 is free, and x1 is equal to 3 halves x2. So letting x2 equal 2, we have 3, 2 is an eigenvector associated with the eigenvalue 2, and we can use that as a basis for the lambda equals 2 eigenspace. We do the same calculation for our next eigenvalue, lambda equals 1. Plugging in lambda equals 1 in here, we get 4 minus 1 is 3, and then we have a minus 3. And since it's the augmented matrix, we're solving the homogeneous equation, we'll put in the 0. Then plugging in our 1 for lambda, so we have our 2, and minus 1, minus 1, so that's minus 2, and then our 0, because it's the homogeneous equation. Row reducing, we get x1 is equal to x2, so 1, 1 can be our basis for the lambda equals 1 eigenspace. So we have two vectors, 3, 2, 1, 1, and since they are from distinct eigenvalues, they are linearly independent eigenvectors, and we can compose our matrix P with the eigenvectors 3, 2, 1, 1, and compose our diagonal matrix using our eigenvalues on the diagonal. So D is going to be 2, 0, 0, 1. And then I calculated P inverse here for your reference, but I just went ahead and wrote P inverse is equal to 1, negative 2, negative 1, 3. And you can verify that A equals P times D times P inverse, except we still haven't solved our problem of computing A raised to the 8th. And at this point, you might think this is more work than multiplying A times A 8 times, but let's just assume maybe this exponent could be even larger, like 124. I kept our P and our D and our P inverse matrices up here. And now we're ready to work on A raised to the K. So A squared is A times A, and I'm going to plug this P, D, P inverse in for A. So I have P, D, P inverse times P, D, P inverse. This is our A times A. Then again, matrix multiplication is not commutative, but it is associative. So I can do the P inverse P here, multiplication first, and that becomes I. So then I'm just left with P D squared P inverse. I can continue and calculate A cubed. That's just A times A squared. So I substitute the P D P inverse for A, and then I substitute what I found for A squared, which is P D squared P inverse. But now, again, I can associate the P inverse with P, and that just becomes I. So I have now P times D squared, which is D cubed, pi times P inverse. And I can continue to do this, but the pattern is that A sub k is going to be equal to P D raised to the kth power P inverse, which then means A to the 8th is equal to P, which is our 3, 2, 1, 1, times a to the eighth. So that, or I'm sorry, d to the eighth. So that's 2 to the eighth, and then 0 and 1 to the eighth, times p inverse, which is 1, negative 2, negative 1, 3. And if you do the multiplication out, you'll get a final answer of 766,510, and the second column is minus 765 minus 509. The second problem, given v1 and v2 are eigenvectors of A, diagonalize A. So A is the matrix, the 2 by 2 matrix with column vectors negative 3, negative 2, 12, 7. v1 is the vector 3, 1, and v2 is the vector 2, 1. The first thing I want to do is to find the eigenvalues for associated with v1 and v2. The easiest way to do this is just multiply a times v1, and note that's equal to 3, 1, which is, so the eigenvalue is equal to 1. If I multiply a times v2, I get 6, 3, so that's just 3 times my original vector, so my eigenvalue is equal to 3. Certainly you can solve the matrix A minus lambda I, but this is, I think, straightforward because it's such a small matrix. So now I can construct P, which will be my eigenvectors 3, 1 and 2, 1, and D that has my eigenvalues on the diagonal. So I have my 1, 0 and my 0, 3. This last problem, let A be a 4 by 4 matrix with eigenvalues 5, 3, and negative 2. Suppose you know that the eigenspace for lambda equals 3 is two-dimensional. Do you have enough information to determine if A is diagonalizable? I have for your reference here the summary of the theorems to determine if a matrix is diagonalizable. Looking through our theorems, of course, first we have the definition. So we'll just check that off because we aren't given P or D. Second, this says if we have an n by n matrix A, so here n is equal to 4, it's diagonalizable if and only if n has linearly independent eigenvectors. So looking at this, we don't know this yet. So we can't quite use this. This one here, an n by n matrix with n distinct eigenvalues is diagonalizable. But here we only have 3 distinct eigenvalues for n equals 4. So we can't use this one, so at least I can eliminate this one. Not appropriate or not applicable. And then last, let A be an n by n matrix whose distinct eigenvalues are lambda 1, lambda 2. In this case, we would have lambda 3. We have 3 eigenvalues less than n. The matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. So let's take a look at that. First, we know every eigenvalue has at least one associated eigenvector. Otherwise, this equation, this is the eigenvector equation, you have to have an x to go with your lambda. And this will imply for lambda equals 5, that has at least one eigenvector associated with it, so the dimension of the eigenspace has to be greater than or equal to 1. Similarly, for lambda equals minus 2, it has at least one eigenvector associated with it, so the dimension of this eigenspace is greater than or equal to 1. And also note, since A is a 4 by 4 matrix over here, these can't be greater than 4. For lambda equals 3, we are given that it's two-dimensional, so the dimension of the eigenspace is equal to 2. So last, since A is 4 by 4, our eigenspace, these dimensions, can't be greater than 4. So we have to have the dimension of the eigenspace associated with lambda equals 5 must be 1. The dimension associated with the eigenspace lambda equals minus 2 must be 1, and the dimension of the eigenspace lambda equals 3 must be 2. So when we add up the dimensions, we're going to get 1 plus 1 plus 2, which is equal to 4, which is exactly the dimension n equals 4. So this is the theorem that we're going to use right here. So the answer is yes. By this last theorem here, A is diagonalizable. In this video, we talked about diagonalization, which applies only to square matrices. So a diagonal matrix is a square matrix whose non-diagonal entries are 0. we noted that powers of a diagonal matrix are easy to compute, and then also if A is a matrix that's similar to a diagonal matrix D, then the matrix A raised to a power is also fairly easy to compute, and it's equal to P, the diagonal matrix to the K, P inverse. We talked about these three theorems that help us determine if a matrix is diagonal. The first one says that an n by n matrix is diagonal if and only if A has n linearly independent eigenvectors. And in fact, those eigenvectors, the n eigenvectors, will form our matrix P, and the eigenvalues will be on the diagonal of our matrix D. Our next theorem said that an n by n matrix with n distinct eigenvalues is diagonalizable. And we noted it's not necessary for a matrix to have n distinct eigenvalues to be diagonalizable. In other words, this is not an if and only if statement. So the converse is not necessarily true. Then we discussed matrices whose eigenvalues are not distinct. So we have this theorem: if A is an n by n matrix with distinct eigenvalues lambda 1, lambda 2, lambda p, where p is less than n, then 1, we know the dimension of the eigenspace for the kth eigenvalue is less than or equal to the multiplicity of the kth eigenvalue. And 2, the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. Then we have this bonus theorem here that says if A is diagonalizable and B sub k is the basis for the eigenspace corresponding to the kth eigenvalue, then the total collection of our basis for our eigenspaces forms an eigenvector basis for Rn. I do have one more slide here, which is just kind of to encapsulate the theorems that tell us when a matrix is diagonalizable. And I did also include the definition. So we know A is diagonalizable if A is similar to a diagonal matrix D. Then this is our first theorem to tell us when a matrix is diagonalizable. And it says that a matrix is diagonalizable if and only if A has n linearly independent eigenvectors. This next theorem says it's a matrix n by n with distinct eigenvalues is diagonalizable. So this is similar to this, except now we can drop the verification that it's independent, because in a previous video when we talked about introduced eigenvectors and eigenvalues, we said eigenvectors associated with distinct eigenvalues are independent. So now when they're distinct, you get the independence for free. So it's kind of the same thing, except it's a way of not having to verify linear independence because you have distinct eigenvalues. This last theorem here then says what to do if you don't have indistinct eigenvalues. If you have p eigenvalues and p is less than n, then the matrix is diagonalizable if and only if the sum of the dimensions of the eigenspaces equal n, and we had an example of that. So that's it for this video. Thank you for watching.